In this video, we're going to start an introduction to vectors. So we're going to look at geometrically defined vectors and some applications. First, let's do some terminology. A vector is a specific quantity drawn as an array. A vector has an initial point, so where it starts, and a terminal point where it ends. We will talk about the magnitude of a vector, and that gives the length of a vector. And we define a vector using both its magnitude and its direction. When we're naming a vector, there's a few different ways we can do this. We can use lowercase bold type with or without an arrow on top. So we see some examples of vectors being named here using just one lowercase letter. You can also name a vector using the initial point and terminal point with an arrow on top. So if I think about a vector having an initial point at P and I want to do my initial point at O and my terminal point at P, this can be named vector OP, so letters OP with an arrow on top. If we call this U, we could write this as vector U, and I can't really do bold very well with my pen, but actually I probably can. U. We could also call this U with an arrow on top. So several different options for naming a vector. Two vectors are equal if and only if they have the same direction and the same magnitude. The resultant is the sum or the difference of two vectors. The resultant is also a vector. So I'm going to start with this image on the right here. If I take vector U, starting at its terminal point, going to its end point, and then adding vector V. So starting at the end point of U and going to the terminal side of V, the vector that connects the starting point of U to the end point of V, that's our resultant. And that's expressed U plus V. Now, if we think about that vector V we just drew, it was going in like from bottom to top, left to right. The opposite of that would be going from top to bottom, right to left. So in this figure on the left, we see we're starting with vector U at its initial point, and then we're adding a negative V. So we're taking that vector V and going in the opposite direction. And now seeing going from the starting point of view to the terminal point of that negative V vector is also a resultant, and that's illustrating the difference of those two vectors. We also have these illustrated using parallelograms, which we're actually going to use parallelograms a lot in terms of creating a resultant. Two forces of 15 and 22 newtons act on a point in a plane. And a newton is just a unit of force that is equivalent to 0.255 pounds. If the angle between the forces is 100 degrees, find the magnitude of the resultant force. So we've got two vectors that we want to represent as forces, and the angle between them is 100 degrees. So I'm going to start illustrating just that. So I want to make an angle of 100 degrees approximately. And then the amount of force is going to represent the magnitude. So we do want one that's shorter than the other. So this first one is going to be our 15 Newton force or 15 Newton vector. And then this bottom one will be 22. Now the resultant is when we combine the two. So what we're going to do is we're going to sketch a parallelogram. And the resultant is going to go from the point where the two forces meet to that opposite angle or that opposite vertex. So here's our resultant. And I'm going to name that just V for our vector. Now, in order to find this, we're going to have to use some properties of parallelograms. The properties we're going to use is that opposite sides are equal. And corresponding angles, so angles or adjacent angles, are going to be supplementary. And just a quick reminder that supplementary angles are two angles that sum to 180 degrees. So we know that the angle between our two forces is 100 degrees, which tells me that the angle in the lower right-hand corner of our parallelogram is going to be 80 degrees so that they are supplementary. We also know that opposite sides have the same length, so I can name the right side of this parallelogram with a length of 15. Our resultant divides our parallelogram into two triangles. We're going to look at that bottom triangle. We have side angle side, which gives us enough information to use the law of cosines to solve for our resultant. So we're going to use the version of our law of cosines that solves for a side length. So our vector squared, and V is just representing the magnitude of that vector, is equal to the sum of my other two sides, both being squared, minus 2 times the product of those two sides times cosine of that opposite angle from the vector we're looking for. So in this case, 80 degrees. So the magnitude of our resultant squared is equal to 22 squared plus 15 squared minus 2 times 22 times 15 times cosine of 80 degrees. If we evaluate this, we're going to get that the magnitude squared is 594.392, and that decimal keeps going. And we're going to take the square root of this exact value. We find that the magnitude of the resultant is going to be 24.38 newtons. The equilibrant of a vector is the vector that goes in the opposite direction. So it acts kind of like a counterbalance from that initial point. So if I have my vector with an initial point V, the equilibrant just starts at that same point but goes in the opposite direction. Find the magnitude of the equilibrant of forces of 48 newtons and 60 newtons acting on a point A if the angle between the forces is 50 degrees. Then find the angle between the equilibrant and the 48 Newton force. So we want to start by drawing our two forces of 48 and 60 newtons with an angle between them of 50 degrees. Now, after sketching our two vectors, those two forces, we're going to complete our parallelogram so that we can see the resultant. And because what we're looking for is the equilibrant of that resultant. So let's complete our parallelogram. Sometimes it helps if you actually turn your page so that you can draw those lines a little bit easier. Yeah, it's not perfect, but that's okay. There's our resultant, which means that the equilibrant just goes in the opposite direction. And I'm going to denote the equilibrant as negative V because we're going in that other direction. All right, so let's go back to our parallelogram and start identifying sides that we know, just like we did in that previous example, setting up this figure so that we can either use law of cosines or law of sines to complete or solve any of these triangles. So I know that opposite sides are equal. And that adjacent angles inside of that parallelogram are supplementary. So I know that opposite sides are 48. And then if we're given the angle between the two forces as 50 degrees, that means the angle adjacent to that is going to be 130 degrees. It does also follow that opposite angles are equal in measure in a parallelogram, but we don't necessarily need that for these applications. So now I can solve this bottom triangle for the magnitude of the resultant, which is equal to the magnitude of the equilibrant. So V squared, my resultant squared, or the magnitude of the resultant squared, is 60 squared plus 48 squared minus 2 times 60 times 48 times cosine of 130 degrees. That gives me V squared is equal to 9,606.456. That decimal keeps on going. I'm just keeping a record of where I'm at, but I'm actually going to take the square root of the exact value to find the magnitude of the resultant to be 98.01, which is equal to the magnitude of the equilibrant. And this is in newtons as well. Now they're asking us to find the angle between the equilibrant and the 48 Newton force. So looking at our picture, we're looking for this angle X, that angle formed between the equilibrant and that 48 Newton force. So we're going to have to use some working backwards. I'm going to now start looking at that top triangle just to illustrate, to work with that triangle that's associated closer with the angle we're looking for. So we know that this leg is 60. We know that this is 130 degrees. We also know that the vector of, or the magnitude of our equilibrant or our resultant is 98.01. And if I look at the angle formed between the resultant and the equilibrant, that makes a straight line, so it's a straight angle. So if I can find the angle between the 48 Newton force and our resultant, then I can use supplementary angles to find the angle we're looking for. So I'm going to call this angle between our 48 Newton force and our resultant angle A. And I'm going to use law of sines to evaluate angle A because I have enough information to do that. So sine of angle A over the opposite side, which is 60, is equal to sine of 130 degrees over the magnitude of the resultant, 98.01. We're going to cross multiply to give us sine of A is equal to 60 times sine of 130 degrees over 98.01. And we can solve for angle A using inverse sine of that expression, 60 times sine of 130 degrees divided by 98.01. And this tells us that angle A is 27.97 degrees. Now, angle A is not what we were looking for, but angle A is supplementary to the angle that we're looking for, which I've named X. So to find that measure of the angle between the equilibrant and that 48 Newton force, we're going to take 180 and subtract 27.97 degrees. And we know that that angle is 152.03 degrees. A ship leaves port on a bearing of 28 degrees and travels 8.2 miles. The ship then turns due east and travels 4.3 miles. How far from the ship, or how far is the ship from port, and what is the bearing from the port? So here we're going back to this method of bearings where all we're given is a degree. Remember that there's two ways to measure bearings. In this particular method, that 28 degrees, we're starting from due north and then measuring that angle in a clockwise fashion. So we're going to start by setting up our picture. We need our port. And on that port, I'm also going to draw my compass to help me set up my bearings. So there's my north, south, east, west. The ship is leaving port on a bearing of 28 degrees. So if I start from that due north and then go 28 degrees and we're moving in a clockwise fashion, there's the trajectory of that ship where this angle is 28 degrees. And the ship travels on that bearing for 8.2 miles. So the length of that segment is 8.2. And then the ship turns due east. So that's moving directly horizontally to the right for 4.3 miles. What we're trying to figure out is at the end of that 4.3 miles on that due east trajectory, how far is the ship now from port? So if we connect that initial side to the terminal side, that's what we're trying to find, X. So in order to solve for X, we need to find an angle in this triangle that we've just created. So we're going to have to kind of work through some other auxiliary shapes to make our way there. I'm going to build a right triangle using that compass, that due north and that due east segment, and that forms a right triangle. And what that allows me to do is figure out that top angle in the right triangle. We know that the bottom one is that 28 degree bearing, and the top angle is going to be 90 minus 28 degrees, or 62 degrees. And now those two angles, that interior angle of our triangle and that top angle from our right triangle, those are supplementary. So that tells me that that interior angle of our triangle is 180 minus 62 or 118 degrees. And now we have enough information. We've got side angle, side, and we can solve for the distance between the ship and the port using law of sines. So x squared equals 8.2 squared plus 4.3 squared minus 2 times 8.2 times 4.3 times cosine of 118 degrees. We get that x squared is equal to 118.837. And that decimal continues. We take the square root of that exact answer. We find that the distance between the ship and the port is now 10.9 miles. And the bearing that we're looking at is, again, starting from that due north from that port to that vector that we're using to represent the distance that the ship is from the port now. So this angle, I'm going to call it y, is our bearing. Okay. Now to find y is going to be 28 plus that smaller interior angle from this triangle. So we're looking at this angle here, which we're going to call W. So the bearing of y degrees is 28, which is that initial bearing, plus that extra angle from those two different vectors. If we look at that triangle, that obtuse triangle we just created, we can use that to solve for W. And I can use law of sines to do that. So sine of 118 degrees over x, but we just found x was 10.9 miles, is equal to sine of W, which is what we're trying to find to figure out our bearing. And that's opposite a side length of 4.3 miles. We're going to cross multiply. Sine of W is 4.3 times sine of 118 degrees divided by 10.9. So our angle W is inverse sine of 4.3 times sine of 118 degrees divided by 10.9. That gives us W to be 20.38 degrees. And if we go back to the top there, we see that our bearing is equal to 28 plus this 20.38 degrees. Or 48.38 degrees.